Hey, Professor.
How's everyone doing?
Doing good. Still trickling in a little bit, but we've got most of the class here.
Yeah, I had a few people mention that they were not going to be able to make today, so yeah, so we'll go ahead and get started. Today I'll go over the homework a little bit just to talk through it and also hopefully everyone has worked their way through it. We'll go over it and make sure that it's all making sense, and then we'll eventually get them graded and turn back to you, of course. But then we'll also talk about the test. And so the first thing here, first order of business is maybe making a final decision on when to have that test. I think we had talked last Friday about shooting for a week from today, the 21st, I think that would be. Someone has pointed out that that is the date of the career fair. And since you all are seniors, that's a pretty important event. So I'm open to making that on Friday, this Friday. I don't want to extend it any farther because we've already covered a lot of material, and we still need to get a midterm in and that type of thing. And so I feel like extending it past next Tuesday would just be counterproductive. Making it this Friday is moving it up. I understand that that's not a fun thing to do if you already have a lot of plans. But I'm also supportive of y'all getting plenty of time to participate in the career fair. So does anyone want to voice any objection to moving it to Friday?
I have something on Thursday and it's like an equivalent of a midterm. So it would be really difficult for me to prepare properly for this test.
Okay. Okay. All right. Yeah, I think we'd want I admit it's a difficult thing. I like to give people plenty of warning on the test. So we'll keep it on Tuesday. I think you still have plenty of time to participate in the career fair, and hopefully you don't have too many other conflicts from other classes that day. So all right, so we'll keep it at next Tuesday then, so we don't have to make any changes there. I believe Dr. Morrow will assist, but I will be available in case there's any questions during the exam. This is the first time I'm teaching this course. It is in my area of expertise, but I never had a chance to teach it previously. And so and given the last minute notice that I was going to teach this course, I'm just unfortunately developing it as we go. If you do see something on a test that doesn't make sense, it's possible I made a mistake. So let's raise that question. I'll be online and available for you. Hopefully there won't be any problems in the test, but that's just how we'll go ahead and do that. Okay, so any questions?
Yeah, is it opening notes or?
So what I normally do here, let's just go ahead and start looking at the exam then. So here, so we're going to cover basically everything up until now that we talked about: random processes, signaling, and receiver design. And the expectations, preview and expectations. Complex formula will be provided. I typically have a little section on my test that right at the beginning that list out a whole bunch of different formula. I'm not interested in testing your ability to memorize formula. What I am interested in assessing is how effectively you can use your tools that you've learned, and the formula, the equations are part of that. What you may have to do is decide which formula to use. I might put a bunch on there, and so you'll need to understand the problems well enough to be able to choose which formula to apply, and you'll have to figure out how to apply it, right? But you don't need to memorize it, right? So I don't, I don't memorize formula in my career. I look them up when I need them. Obviously, once you've used them a few hundred times, you start to memorize them just by default. But that's why we have search engines. So now I want to help you get a fair grade on these exams, and but in order to give partial credit, it's necessary for me to understand your thought process as you approach a problem. So even if you can't figure out how to get all the way to the end, please explain your work, right? Not just show your work, but explain your thought process of what you're doing. And if you get the problem set up correctly, but can't figure out how to finish, that's a great start. And I will I'll try to give you an appropriate amount of partial credit. That tends to be a final decision on my part as I grade the test. I put a lot of effort into grading exams. If afterwards you see that I've made a clear mistake, I want to hear about it, and we'll get things fixed. I don't tend to get into negotiations over the amount of partial credit on a grade, so just set that expectation up front. Now, I also tend to run my test where I try to give you some easy questions to answer, so you get a good start at things. Those tend to be like, fill in a blank, or multiple choice type of questions to understand your knowledge and understanding. Don't take that lightly, though, because those type of questions are hard to get partial credit for. So if you don't know the material, and I think I've given you an easy question to get some baseline points, you haven't really studied the material well, you're going to lose points on easy questions. So please don't do that. Make sure you're prepared for this. So all right, so now let's get into these what I'm expecting you to be able to answer on the test. So this is a preview. Doesn't mean I'm going to ask all these questions. Doesn't mean I'm going to ask them in a particular way, but I will base my test upon this, right? So describe what is meant by entropy in information theory, and explain what Shannon's capacity theorem means, or its significance, right? So we talked about that in the early lecture, I think. So let's see if I can get my camera working here. Let's see, let's stop that and change to my other camera. All right, I still do not have a great setup for these recordings, but yeah. All right, so Shannon, capacity is basically C is equal to the bandwidth times the log base 2, because we work in bits, right? And then that's 1 plus the signal power divided by the noise power. And this is in bits per second. So this is our capacity, right? And so, come on, you're supposed to focus. Okay. And so the significance here is that we can get more information across if we use more bandwidth, or if we use more signal to noise signal power, or if we can minimize the noise somehow, right? So if we increase B or S, we get more capacity. If we decrease N, we get more capacity, right? So, and maybe an easy way of looking at that would be, let's see if I can figure out, maybe this presentation has, it's actually lecture 6, I should fix that. So if you look at some constellations, right, then you can understand that in this type of constellation, this is 64 Comm, right? And that means that for each symbol we're sending out, we're actually sending 6 bits, right? But that requires pretty good signal to noise ratio, right? You see here there's a signal to noise ratio of 28 dB versus 22 dB. If we drop much below 22 dB, you can see that we're going to start getting confused about which symbol was actually received. Let me ask a question. Have you covered decibels in your previous work, right?
Yeah, I did.
Okay, just making sure. So as we know, a decibel is a ratio 10 log of the power ratio, or 20 log of a base 10 of the voltage or amplitude ratios, right? But so the so we can see visually when we look at these constellations that if we have a good signal noise ratio, we can go to a higher number of K bits per symbol transmitted, right? Or we can simply use more bandwidth, right? So that's important to understand. The first time we looked at this, we just kind of presented it as is, but hopefully now you've seen how you can implement some of these trade-offs to get more capacity in a channel. The entropy concept, that's a measure of the new information that you're sending. All right, so if there is no randomness or uncertainty in the information. If it's already known, then there's no need to communicate it, right? But if there's a high degree of uncertainty or entropy, then we have a high degree of information gain when we communicate that data across, right? So, okay, let me go back. All right, so describe the purpose of a given block in the communication system. So I will let me actually well, I thought I had that up. Okay.
Do we need our laptops to take the exam or no?
No, I don't think so. Okay. It was in lecture 2 here. Yeah, and there's my share button. So in lecture 2, we talked about these different parts of the communication system, and we've been focusing here on the channel modulation, talked a little bit about the channel itself, and we've been talking about the digital demodulator mostly, but go ahead and study these slides here and understand what each of these blocks do in concept, right? Okay, identify the features of a signal, otherwise also known as a carrier, that can be modulated to carry information, right? So, basically, how do we form up a symbol, right? Do we modify the amplitude, the frequency, or the phase, or some combination of those, right? So we looked at like a cosine, a cosine omega t plus phi, right? And you can modify any of those in a structured way in order to encode information such that at the receiver can examine that feature of the signal and estimate what information was sent. What are some examples of randomness in a communication system? We've mostly looked at in our calculations our additive white Gaussian noise, but we've also noted that there's a bunch of other randomness in a mobile communication system. You're constantly moving, and so the path length is changing. If you're driving along the road, that is maybe has a very strong trend to it. But if you're holding a handheld communication device and you're kind of waving it around, you're getting all sorts of noise there due to the changing path length, right? And so as the signal travels from transmitter receiver, it is going through a certain distance. We can measure that distance in wavelengths. Wavelengths are, also in a one directional path, equivalent to 360 degrees or 2 pi radians. So little changes in that distance between transmitter and receiver will manifest itself in changes in phase. Other type of examples are, let's see, the rate of calls started at a particular base station, right? So that is a function of the number of users in the area and how often they're starting call sessions or data sessions or something like that, right? So lots of different potential things. Another one that's important to understand is this multipath interference. We haven't really looked at the fundamentals of it. I just kind of described it, but maybe I can show that real quick here. The idea that if you have a transmitter here and a receiver some distance away, and there's a big mountain here, and you have a signal that reflects off of that mountain, but you also have one that travels directly. You might actually have one that bounces off the ground, or some building or that type of thing, right? So each of these has a different length, right? So we learned from high school geometry the shortest distance between 2 points is a straight line. So this is going to be have a delay of tau, but this is going to have a delay of tau plus delta tau, let's say, right? And so these reflected signals will go through a longer distance, a longer time. That means their phase is going to be a little bit different. If they arrive here with two signals, x1 of t is going to equal a times cosine omega t plus phi, and then we'll call this one x1 and this one x2. X2 of t might be a fraction of a. We'll just call that little a times big A, right? So that's it's going to be reduced because one, well, it's traveling a farther distance, but two, it's reflected off something and probably lost some energy in that process, right? But it's going to also have an omega t plus phi plus delta phi, right? And so if delta phi is on the order of pi radians or 180 degrees, then these signals will cancel, right? They're going to add or subtract based upon that phase, right? So there you can draw these things out as vectors, and they're going to add and produce a net vector that may or may not cancel. So at times it's going to be potentially stronger, and other times it's going to be potentially smaller. So another important, and we call this multi-path interference because there are multiple paths to the end, and they are interfering with each other, or constructively or destructively interfering with each other. Okay, so let's go back to our preview here, and So understand what a probability distribution function is and its limits, right? And understand what a probability density. So just understand a distribution function and a density function and their characteristics, right? So a distribution function again is going to you're going to have some probability and it's going to approach 1 up here, and it's going to be 0 down there. And this is that cumulative probability. So really what we're looking at is our random variable less than some value, right? Where this might be alpha, right? So then that would include all this distance back here, right? Whereas a probability density function is now, you know, could look like this, right? This is a you know, trying to be a Gaussian distribution, and sorry, you got to pop up here. If you integrate this whole area, you're going to end up with a probability of 1, right? But if you integrate over a particular range, that's going to give you that probability that your random variable falls within this range. A thing to note with continuous random variables, that the probability that it's any given point is really 0, right? The probability for a continuous or continuous random variable being a specific value is vanishingly small, right? Because you can keep dividing that interval to a smaller and smaller amount, and that probability goes to 0. So when we're talking about continuous random variables, we tend to talk about a range, right? So it's greater than or between or less than or something like that. All right, let me so, and we can differentiate the PDF to get the distribution function, or we integrate the distribution function to get the PDF, right? Do I have that the right direction? I'll check my notes. So find the mean and or variance of a random variable given its probability density function, right? So yeah, so we actually I did have those backwards, right? So we're going to differentiate the distribution function to get the density function and vice versa. So so find the mean and or variance of a random variable given its PDF, right? So and also potentially a function of it, right? So and I think we talked about that in one of the early classes. So but that should be something that you've covered in previous courses, right? So conditional probability and Bayes theorem, you did a homework assignment involving that, so we use that in communications a lot to switch, as we saw, switch between post a priori and a priori type of conditional signals, right? So then I think this is new material here. Describe the conditions for a signal or system to be wide sense stationary. Well, obviously it has to be a random process to begin with. The wide sense stationary is important to be able to claim, and that's because then we don't have to worry about absolute times. We're dealing with the difference in times, right? So again, you did a homework assignment on that, and those implications. Describe what is meant by ergodic, and that's where the idea, if we have a random process, that's going to any given sample out of that process is going to evolve over time, but that you can also draw different processes or samples from that random process, right? So if you repeated an experiment over and over again, you might get different, you will get different series of processes coming out of that, or samples. So ergodic means that we can look at the time averages of a given signal and use that as our sample averages. So whether we sample different ones or we look at a single sample over time, we can get the same statistics. And obviously that is very convenient also in our signal analysis, because we can just look at something once and understand its statistics. Okay, how many symbols does it take to communicate if k is equal to 4, right? So when we start looking at modulation, we looked at the type of systems that might send more than one bit at a time, and so we know that that's related through a log base 2 type relationship, right? So for example, if we group together 3 bits, then we would need 8 different symbols, or 2 to the 3, 8 different symbols to transmit that information, right? But we only have to send one symbol at a time, but we need 8 different ones to choose from to represent all the different values that those 3 bits can take on. So if we're starting from a number of symbols, it's that's, let's say m equals 16, we take log base 2 of 16, that is 4, right? So we can encode k equals 4 bits for that number of symbols, right? So
I can't see the.
okay, can you see that?
Hold on, sorry, you're still sharing your screen with the test. Trying to figure it out.
Yes.
Sorry, there you go. So k equals log base 2 of m. So again, if this is 3, this is if k is equal to 3, then m is equal to 8, right? Or we can write this as that type of relationship also, right? So all right. Okay, so how many bits are, just some examples. How many bits are transmitted by each symbol in a 256 QA system, right? So there's M is equal to 256. Each symbol can therefore transmit log base 2 of 256. So that's 8, right? So so then you can translate between symbol rate and bit rate, same, but with energy. So bit rate and symbol rate are related by K and M. So you did a homework assignment on that for the rates. And also you can do look at that same thing with respect to energy. So if it takes a certain amount of energy to transmit a symbol in a 8 QAM type system, then each bit K is equal to 3 in an 8 QAM system. So each of those 3 bits kind of uses up a third of the energy that symbol is consuming.